merci. So let me switch to English and hello everybody. Welcome to this session of a mathematical physics seminar of IPHT. So today we have the pleasure to welcome virtually Hugo Duminil-Copin from IHES in Geneva. So allow me just to say a word about Hugo. Hugo did his PhD in Geneva under the supervision of Stas Smirnov, and after that he became gradually. I read your CV, but a postdoc and then assistant professor, and now you are full professor in Geneva. And since 2016, you are also a permanent professor at IHES. And as weird as it sounds, you never came to Saclay to give a seminar, so that's what I am hoping to, at least virtually, to fix.
And
today.
I still didn't, apparently.
So let's fix that today. And just to say a word about your work. So you work in many fields in statistical mechanics, percolation, I noted, Ising model, Potts model, in 2 dimension and higher dimension. You are also famous for proving the prediction of Ninois that the connective constant of a honeycomb lattice is equal to square root of 2 plus square root of 2. And recently you worked also with Eisenman to prove the triviality or Gaussianity of the Ising model and phi-4 model in 4 dimensions. And so today we have the pleasure to hear you talking about emerging symmetries in 2D statistical physics. Thank you.
Thank you very much for the nice introduction. And I promise I will come to give an in-person seminar at some point. I'm sorry if I couldn't do it this time. Yeah, so I was hesitating about the subject that I would describe because I could have spoken about the 4D easing result with Michael, which I think is of course relevant to physicists. But I thought I would talk about something a little bit newer, a more recent project, which is actually an ongoing project. So I'm going to explain to you one result that we got, which I kind of consider as the first step of a program. And the motivation for this program is to try to get conformal invariance of a large class of 2D models. So, I mean, I'm not going to tell you too much about that because you, of course, know about it much better than I do. But DPZ conjectured conformal invariance of the scaling limit of critical systems. And in 2D, it's a particularly strong prediction because it allows a classification of the different conformal field series that one can get. But I mean, so this on the physics side, it's a very successful story, let's say. But on the mathematical side, there is one missing step in some sense, something that is actually very hard to achieve, but which is almost like an axiom on the physics side. I mean, depending on which field of theoretical physics you are in, which is that it's difficult to get that just a lattice. I mean, difficult to prove that a lattice model itself converge when you take the scaling limit to a conformally invariant object. Once you have the conformal invariance, you can say a lot of things, but it's difficult, in general at least, to prove that a given discrete model converges to a conformally invariant object. This is really a challenging task mathematically. In fact, it's so challenging, so there are a few exceptions where we did indeed manage, I mean, we meaning mathematicians, managed to prove conformal invariance, and these, like very few exceptions, actually I mean, brought fame in some sense, instant fame to the people who achieved this breakthrough. Okay, that's not good. I don't know why I have so little battery, but anyway. So just let me mention that the Ising model is famous to, I mean, to have been proved to be conformally invariant by Stas Smirnov, and actually also with work with Čerkák. This was roughly in 2008. there are the dimers, the dimers by Kenyon. Sorry, I'm a little bit worried about the amount of battery I have. So I mean, Kenyon in 2000 proved conformal invariance of dimers. And then let me give you a third example, which is a Bernoulli percolation, which I will tell you what this is in a second for people who don't know, which was proved to be conformally invariant by Smirnov in 2001 in this famous paper where he proved Cardy's formula. When you look at this list, so there are a few more examples, but which maybe would be a little bit less appealing to physicists because they are a little bit more like obvious discretizations of a continuum object. But when you look at those examples, Ising, dimers, and Bernoulli percolation, you quickly realize that there are specific models that, I mean, there are models that have specific integrability properties. So I guess that in IPHT, you all heard several times about integrability. So I'm not going to redefine these things, but the Ising model in some sense, and dimers is kind of a discrete version of free boson. So there is a determinantal structure behind this, and Ising is kind of free fermions where you have also a structure where naturally Pfaffians appear and you have like many properties that are especially good. Bernoulli percolation is a little bit less clear why it has nice integrability properties, but on the probabilistic side, there are big simplifications when you look at this, and on the physics side of integrability, you have QKZ and this kind of thing. So you have additional integrability for these models. And the problem is that these models describe only 3 universality classes in the whole, 3, if you want, central charges for your conformal field series. And you would like ideally to be able to prove conformal invariance for representatives of every conformal field theory possible. At least here, because I'm looking at statistical physics model on a lattice, I'm interested in central charge between 0 and 1. So here, so the goal is to try to understand, and I'm going to insist on this try because so far we do not succeed, of course, otherwise I would be already telling you about the results. So try to prove conformal invariance of a large family of lattice models. And ideally, when I mean large family, I mean maybe a family that contains in it a representative of different universality classes that you can get. Okay, so for now, this was just the motivation, for the start of the talk. But let me now tell you a little bit more precise description of the goal and of the objects I'm going to look at. So precise description. So let me first tell you about the family of models we are going to look at. And you may disagree with this choice, but I'm going to try to motivate it later on. So I'm going to look at the percolation model. So what is a percolation model? I imagine I work on Z2, say. And the goal is to pick a random subgraph of Z2 where I have the same vertices as the original graph, but I take a subset of the edges. So I'm going to represent this subgraph omega, let's call it. So it has a set of vertices and a set of edges. So V would be the same thing as Z2, or the same thing if I take a subgraph of a finite graph, maybe G is a finite subgraph of Z2. So V would be the same vertices as the vertices of G. And E would be seen as a set of edges in G such that omega E equal 1. So I think of omega as a function from 0, 1, from the edges to 0, 1. 0 if my edge is not in my subgraph, and 1 if my edge is in my subgraph. It's a way of encoding a subgraph of my original graph. Now I need to tell you how I pick this subgraph at random. And I'm going to do it like that. So I'm going to define the measure, which is going to depend on a few parameters. So one is going to be P. So the probability, so I'm giving you the probability of a configuration. So I'm going to start by putting P to the number of edges, 1 minus P to the number of edges that are not in omega. So here omega is by definition the sum of the omega E. So it's just the number of edges in omega. So I'm just putting P to the number of edges, 1 minus P to the number of edges I didn't pick. Okay. If I stop like that, I end up with a model where you can interpret basically the model as I pick an edge. I mean, each edge is picked at random independently with probability P. So I pick an edge with probability P, I remove it with probability 1 minus P, and I do this independently for every edge. I end up with exactly this measure. Okay. So this is called Bernoulli Percolation. But I'm going to make the thing a little bit more interesting by adding another parameter Q and putting Q to the number of connected components in omega. So when Q equal 1, I end up with the same model. And when Q is not equal to 1, in particular, when it's larger or equal to 1, I'm kind of favoring that there are many connected components in my graph. We call them sometimes clusters, because maybe I will use this word without really noticing. And if I do it like that, I'm actually doing something a little bit wrong, because this is not a probability measure anymore. It's a finite measure, but not a probability measure. So let me renormalize it by a constant. So this is going to be a partition function, if you want, or a renormalization constant, in such a way that now this thing is a probability measure. So now I pick at random omega with this law. Okay. So this, let me maybe repeat it here, that we keep it. Okay. So this is called the Fortuyn-Castellan percolation. And you can try to draw the phase diagram of this thing. You put P and Q. And what you realize quickly is that what happens is that there is a curve. Oh, that's a terrible way of drawing it. Sorry about that. Let me start like that. There is a curve which is actually this curve, P equals square root of Q over 1 plus square root Q. And this curve is separating two phases, a supercritical phase, where in fact, when you define, so here I defined it, if you look at the definition here, you realize one thing, which is that it makes sense only in finite volume, if G is finite, because we have this P to the number of edges, 1 minus P to the number of closed edges, and even this Q to the number of clusters. If I'm on an infinite graph, all these numbers are going to be infinite. So it's going to be very bad to define this object. But what you can do is first define it in finite volume, and then let's take a limit when G tends to infinity. The measures themselves, they are going to converge to a limiting measure defined on Z2. And on this measure, when you look at the supercritical phase, what you end up with is that there exists an infinite connected component almost surely. There is a lot of small things here. And in the other regime, you get a subcritical phase where this time you get no infinite or all connected components. Every connected component is finite almost surely. Okay, so it's two phases that, at least from a physics point of view, at first sight are not so interesting. I mean, there are actually nice things to tell about that, but it's not going to be the object of this talk. What we are going to be interested in is really what happens on the critical line. And here I should start by saying that I'm doing something bad, which usually mathematicians don't really notice, but here in front of physicists, I'm going to be careful about that. It's not really a critical line. It's a critical line up. So let me remove that. No, oh, that's not what I meant. So let me remove it. It's a critical line up to Q equal 4. In the sense that here, really, when I look exactly at P equals square root Q over 1 plus square root Q, I am looking at a critical system, meaning the correlation length is infinite. And in fact, we are going to expect conformal invariance. Above it, you have actually a discontinuous phase transition. So I'm not going to focus on this phase because you don't have a conformal invariance limit there. There is a correlation length at criticality, and it's just this. I mean, there are like coexistence of phases that are different, like a supercritical and subcritical phase in some sense. So this is not going to be interesting for us. So we are going to focus on Q, in fact, between 1 and 4, but the not going to 0 is just to state something for the, but I mean, actually our thing would work up to 0, so it's not a very big restriction. So Q between 1 and 4, and P equal what we call the critical point, PC of Q, which is square root Q over 1 plus square root Q. So we will focus on this. Now we want to be describing the behavior at this value. Oh, by the way, why did I, maybe first, why did I focus on this class of models? For several reasons. The first one is that these percolation models, they are related to a bunch of other models. Oh, that's very bad. I think I just lost my, okay. That's bad. So what do we do? I don't understand. I charged it the whole night. So could restart, it will be good. Well, I have a backup plan, but it's not a very good one. I mean, if you could just restart, it would be good. Okay, why it's starting, I mean, trying to restart, it's putting that it's 100%. I don't understand what is happening. Why it's trying to restart, let me finish what I was saying about this class of models. So these percolation models, they lie at the crossroad of many other models. So they are related, for instance, to a class of models you know very well, which are the 6 vertex models. So these are models of arrows that are defined on a lattice, and they are very natural because they are related to height function and they are related to better ansatz, so to integrability in a very strong fashion. So there is a clean coupling between the two, which is called the Baxter-Vu-Kellen coupling. So if you get something on FK percolation, you end up with something on 6 vertex. So in particular, I will explain that we get rotation invariance of this FK percolation. You end up with a rotation invariance of the 6 vertex model. It's also related in another direction to Potts models. When Q is an integer, if Q is equal to 2, it's related to the easing model, the 2-state Potts model. If it's equal to 3, Q is equal to 3. Okay, okay, it seems like I lost my iPad, so I'm sorry about that. It's fine. I'm going to jump just to another. I had slides. They are going to be in French, and they don't quite say what I want, but I'm going to juggle with that. I'm really sorry about this thing. I know that somebody hates Zoom, but it's not due to Zoom in this case. It's due to apparently the charging mode of my iPad. Sorry about that. Do you see slides here?
Yes, we
okay, so I'm going to juggle. I think all of the information is on my slides. They are in French but I'm going to describe them in English. And then it's not quite what I wanted to say, but at least I can juggle between the different things. So let's, for now, stay here. So just let me finish what I was explaining, and I'm really sorry for this screw up. So yeah, so when Q is an integer, 2, 3, or 4 in our case, these are the 3 values of interest, it's going to be related to the Q state Potts model with Q, which is just 2, 3, or 4. So in particular, if you get rotation invariance of FK percolation, you get rotation invariance of the Potts models. And the last thing I wanted to say, and so it's also relating to Ashkin-Taylor, for instance, models. I mean, it's related to a bunch of models. The last thing I wanted to say is that these models in the scaling limit, which I'm going to describe now, they are going to converge to conformal invariance objects. And these objects are parameterized by a parameter, and varying the Q is going to vary this parameter continuously. And it's going to describe basically a whole range of possible conformal field theories. So that's why we are interested in this, because within this family, you can describe a whole range of conformal field theories. So let me tell you what we are going to be doing exactly. So we want to be describing the model at criticality. So what I'm going to do is, in order to have a pictorial thing, so I'm going to take the scaling limit, which is something you know very well. You take your model not on Z2, but on delta times Z2. With delta is the mesh size of my lattice, and I'm going to try to let delta go to 0. Very good. But in order to kind of, I mean, a random subgraph of delta Z2 when delta tends to Z2 to 0, it's not so clear what is the kind of objects that would arrive in the limits. So what I'm going to do is I'm going to simplify things. I'm going to only look at boundary walls in my model, meaning the boundaries of my clusters, of my connected components. So I'm going to describe this. I'm going to take the boundaries. Here, I only drew the boundaries of the 4 biggest clusters. But you draw the boundaries and you end up with a family of loops. You do it for all loops, all connected components. You draw all the boundaries. And you get a random collection of loops, and you want to understand how this random collection of loops behaves when delta tends to 0. Okay? Okay, so in order to be fully rigorous, I need to tell you when I speak of a convergence of a family of random loops, I need to give you a topology on the family of loops that you can speak of convergence in law. Okay, so in order to speak of convergence in law, what I'm going to do is I'm going to define the distance. And the distance between 2 families of loops, F and F prime, is going to be smaller than epsilon if whatever the loop in the first family, which has a radius at least epsilon, there exists a loop in the second family, which is close to this first loop. But when I mean by close, I just mean that maybe you can parameterize the 2 loops in such a way that the function that you end up by parameterizing, they remain at distance epsilon of each other. Okay, it's not a very big, I mean, it's not a brilliant definition of a distance. If I would, you know, I mean, kind of put you in a room and forbid you to exit before you end up with a distance, you will actually quickly reach this distance as a natural distance for between 2 loops. So there is a distance between 2 loops. And now the question is, what happens when omega delta, so you can speak of a convergence in law, and you wonder what is the limit of omega delta when delta tends to 0. Okay. And
Hugo, there is a question in the chat by Andreas Portiello. Can you use height functions instead?
That's a good point. As soon as you have a family of loops, you can define, you can orient them, let's say 1/2 in one direction, and it gives you naturally a height function. It's indeed something very natural to do. The thing is that this, I mean, you could define then a distance between the height function in a more classical way. Maybe you integrate against smooth function and you see how close you are. The problem, if you do that, will not come from the definition of the distance. It's perfectly fine. And by the way, the distance I just defined would actually be stronger than the other distance that you would define naturally directly on height function. So the bigger problem is that actually the height function itself that you end up by orienting these loops, 1/2, is not very natural except for q equal 4. For q equal 4, it's a very natural height function. It's actually going to converge, that's the prediction, to Gaussian free field. For the other values of q, actually the natural way of attributing a height function would be to complexify things and actually each loop to write. So each loop contributes, in fact, square root q. When you write only at criticality, if you write the thing only in terms of loops, you end up with a very clean expression, which is the probability of a loop configuration is proportional to square root q to the number of loops. So this square root q, if you write it lambda plus lambda bar, where lambda is a complex number, then you can expand in oriented loops. I mean, clockwise would correspond to lambda and counterclockwise to lambda bar. And you have a kind of natural complex value, I mean, complex weighted height function. But you see, I mean, this is not going to be so easy to actually describe the scaling limit. I can go back to this at the end if you want more details. But I mean, it's possible, but it's not necessarily helping so much at this stage, at least. But it's, I mean, it's very natural to think of a height.
Question.
Yeah.
Sorry. Your definition of distance is quite different from the usual definition among two subsets of a metric space. I mean, you take both gamma prime, and you run over them at the same, say, time. I mean, I would have seen something like max over t, which runs over gamma primes, and t primes, which runs over gamma. You understand?
I mean, maybe it's, I mean, the answer is hidden. So this is kind of the global distance. It's hidden here. You are allowed to parameterize as you want. So what I'm saying is that find the best parameterization possible. So if you take an arbitrary parameterization, then what you say is roughly what you are doing. That, okay, maybe you didn't parameterize right. So what you just mean is that you can find a function t prime in terms of t that then you remain close to each other. But that exactly corresponds to parameterizing the second loop smartly in the first place, that it's exactly coinciding. So I think actually the definition is matching what you have in mind.
What I'm saying is that you do not you use a smart configuration. I mean, you do not maximize over all possible parameterization.
You minimize over all maximum.
Yeah, you minimize, but so if you say that something is smaller than epsilon, it means that you have parameterization which are not smaller than epsilon.
So
it's not uniform. It's not uniform, what I will say.
It's not uniform. Okay, I'm not getting what is your concern, but I think actually it actually matches exactly what you would like to do. So the shapes, the traces are close to each other, basically. That's what.
Okay.
I mean, we can rediscuss that at the end if you want. Okay, so we can speak of the limit when delta tends to 0, and let me tell you very briefly, because this is something I spend more time on when I'm describing it to mathematicians, but to physicists, this is going to sound a little bit more, let's say, classical. So what you, as a physicist, would do is you would actually conjecture that omega delta, when delta tends to 0, converges to something, to an object in the continuum, which I will call omega continuous. And you agree with me that as soon as you make this assumption, actually scale invariance and translation invariance of your system come for free. Just from the existence of the limit, you know for a fact that you immediately get scaling and translation invariance. So I will not describe it more, But then a more interesting kind of property of the limit that you would like to get is that you also expect the thing to be rotationally invariant. And this is much more subtle, maybe the first time you see, because if you think about how you would justify the existence, I mean, the rotation invariance of the thing, you will actually refer to the renormalization group probably. You would say, you know, I mean, it's kind of universality that is going to give you this rotation invariance. If I start from a lattice or a rotation of my lattice, I end up with the same limit. And I justify this by saying that in the renormalization group, if I start from different lattices and I iterate the renormalization action, I'm going to actually end up to a fixed point. And, you know, if I'm lucky enough, this fixed point is unique. So I will always end up with the same thing, right? I mean, I think that's probably what a physicist would argue over lunch if I ask him, you know, how do you justify rotation invariance? But of course, I mean, justifying the uniqueness of the fixed point is actually a difficult thing mathematically. So I will come back to that later. And then once you have these three invariances, then it's very natural to expect to end up with conformal invariance. I'm sorry that the slides are in French and that I have to skip certain parts, but you have more knowledge than mathematician on most of what I'm going to describe. So I need to skip things, and I use flattery to try to to get away with the screw up with my iPad. So if you have these invariances, then you kind of expect actually conformal invariance, right? And conformal invariance in the setting of my my loops. Let me tell you what would happen. So if I take, it will mean the following: if I take a domain omega, and in this domain I do the square lattice with very thin mesh size, then I can construct in the continuum a family of loops by taking my discrete percolation model on this very fine mesh size lattice and letting the lattice to 0. I will end up with a family of loops. On the contrary, if your favorite domain is another domain, which is imaged by a conformal map F of the original domain, then there you can actually play the same game, start with the square lattice and take the limit, and you end up with a red family, a family of continuous, a continuum family of loops. But what you can also do is just take the family you end up with on the left and use a conformal map to conformally map it to the new place. And what conformal invariance means is that the two objects have the same law. Okay, as random objects, they are the same. So this is clear when you use rotation invariance, scale invariance, and translation invariance. But here we mean that this is true whatever the conformal map. And once you are there, in some sense, you have an object, a conformally invariant object, which is that defined that you end up, you can actually describe what is a family of loops very precisely. It's what we call a conformal loop ensemble of parameter kappa, and kappa is a function of Q. Remember, we had a parameter Q and a parameter P. We are at the critical, imagine you are at the critical point for a given Q. Then when you do the scaling limit, if you expect conformal invariance, you end up with a family of loops, which is a conformal loop ensemble of parameter kappa. And this kappa, just for your culture, is 4 pi over pi minus arc cos of square root Q over 2. It's a weird function, but the important thing is that it varies when Q varies, and it gives you a description of a large family of conformal loop ensembles, basically all those from parameter kappa between 4 and 8. So it's and it corresponds to conformal field series, this conformal loop ensembles. So this is basically the dream would be to get this this conformal loop ensemble convergence. Basically, you describe the limit of this. By the way, for people who are more used to, say, local operators, local observables, and so on, because here you have family of loops, you don't have attached points, and so on. Just if you are with Ising or Potts models, once you get conformal invariance of these loops, you can get conformal invariance of spin-spin correlations, energy-energy correlations. If you like the 6-vertex model, you can get conformal invariance of correlation between the gradient of the field at different places. This will be correlation between arrows. You can get many things out of this conformal loop ensemble convergence. So once you are there, you are very happy. Okay, so at this point, it's the end of my the first part of my talk, and it's already 40 minutes in, so I'm not in trouble at all. But what do I want to say now? So clearly, I'm not here to announce that we know how to prove this result, yet at least. But I want to be advertising two strategies towards this result. Because these two strategies, I mean, one is going to be very natural and maybe not that, that enlightening for you. And the second one will be maybe a little bit more surprising. These two strategies, they are going to rely at some point on one thing. And this thing we know how to prove. So we don't know how to achieve the strategies, but we know how to prove it. So the first strategy, this one I can show it a little bit because it's here. So the first strategy is going to be to follow basically I would call the historical steps towards conformal invariance on the physics side, which is to imagine this as first, you prove that there is a scaling limit, that omega continuous exists, that you can take the limit when delta tends to 0. And this limit, a good thing about it is that you get for free rotation, scale and translation invariance. This comes for free. So the only difficulty, only with a lot of guillemets, so this will give you the scale and translation invariance. The second step is to prove rotation invariance of this scaling limit. This a priori, you don't really want to be doing it using universality. I mean, you definitely want to, but it sounds really like science fiction from the mathematical point of view to be able to justify universality at this stage. So you want to find another argument that would give you rotation invariance. And then there is this third step, which is, well, once you have these three invariances, translation, scaling, and rotation, maybe you can actually get conformal invariance out of the three. Okay, first step, I have zero clue how to do this existence of a scaling limit. I mean, okay, I mean, I want to believe that as the physics part in me, physicist part in me would definitely say, this omega delta has no reason not to be a convergence sequence. So this is a reasonable assumption. And then I can try to spend time on the two other things because, I mean, in full honesty, I don't know how to justify this scaling invariance. Then there is this rotation invariance, and this is going to be actually exactly the result that I'm going to describe, that we know how to prove rotation invariance. And then there is a third step, which is this: once you have these three symmetries, you end up with conformal invariance for free. And this, to be honest, we have fairly good hints why this is true, and that doesn't seem like full science fiction. I mean, this seems like a reasonable thing to manage to do in a few years. But there is this first step, which is very problematic. So that's strategy one. You follow the historical steps in the sense that you first assume what was probably assumed first, which was the scale invariance of your model. So it's a scaling hypothesis for critical systems. Then you use rotation invariance, which is maybe a byproduct more of the renormalization group development in the end of the 60s. And then you have this conformal invariance prediction, which is very much kind of what Belavin, Polyakov, and Zamolchikov did, which is like the thing is local, so if it should be invariant under any map, which locally is a composition of the three invariances. And the first step seems to be the hardest step. By the way, it's not what I thought. We tried to prove the first step, and we end up with the second one. The second one sounded to me much more mysterious, this rotation invariance. Anyway, let me mention the second strategy just for because that's actually the one we are really trying to achieve, is that you start with rotation invariance, you prove rotation invariance, and what happens then is that it seems, and I don't know how much this is true, but we are advancing quite well, to be honest. We don't have a full result, but we believe that actually the rotation invariance gives you a lot of information on the spectral properties of the transfer matrix of these models, in particular of the transfer matrix of the 6-vertex model. And we believe that there is a chance that we can identify basically how the spectrum behaves in the bulk, not at the very top of the spectrum, but more in the bulk. And that should be sufficient to get Gaussian free-field convergence of the height function of the 6-vertex model. This is already a very strong indication that you get conformal invariance of the loops of the random cluster model, because the Baxter-Wu coupling between the 6-vertex model on one side and the percolation model is kind of giving a lot of information already on the percolation model. So we expect, again, a 3-step strategy. The first step will be rotation invariance. The second step will be understanding from it the spectral properties of the transfer matrix of 6-vertex model and get the convergence to Gaussian free-field for the height function. And then third step will be to bootstrap this information through the Baxter-Wu coupling to get conformal invariance of percolation models. So this strategy actually seems to us more reasonable than the first one, but notice that there is a common denominator to both strategies, that we need to prove rotation invariance somewhere of the model. And this is, let me jump, this is, why is there so, okay. This is exactly the subject, I mean, the theorem I wanted to describe in this talk. Forget about the top side here and just focus on this. So what this thing is saying, and this is our result, is that there is a natural definition of distance between measures this time that you can define, which is in some sense the distance between two measures is small if you can couple the two measures, if you can make, make the two measures on the same probability space in such a way that the distance between the loops that they create are very close to each other in the sense of the distance between families of loops that we defined before. So we define the distance between families of loops. Now, if I pick loops at random, I'm going to say the two models, like model 1 and model 2, are close to each other if I can basically make them in such a way that with very good probability, the distance between the family of loops is small. This is a very natural notion of distance in some sense. So here, I mean, it's more formal, but it's saying exactly that. If I take two families of loop P, I mean, two models of loop P and P prime, so I pick, say, F according to P and F prime according to P prime. So F and F prime are random families of loops. I'm going to say that the models are close to each other, they are distance epsilon. If with probability 1 minus epsilon, I can make them in such a way that the distance between the families of loops is smaller than epsilon. It's really just think it's a way of measuring how close two statistical physics model of random loops are. And now the theorem says the following. The theorem says, if I take delta small enough, then the distance between, say, the loops that I create by looking at Fortune-Castellan percolation on delta Z2 and the family of loops that I create by doing the same on a rotation by an angle alpha of delta Z2, where the distance between the two is polynomially small or algebraically small in delta. So the smaller the delta, the smaller the distance. Really think the model is becoming asymptotically when I look, if I don't rescale by delta, but I look at larger and larger scales on Z2, it's looking more and more rotationally invariant. Okay. In particular, it tells you that if you take any subsequential limit when delta tends to 0, you get something fully rotationally invariant. Okay. So that's what the theorem is saying. It's just giving you rotation invariance, if you want. And we don't even need to assume the existence of omega continuous. We get it just quantitatively when you look at a large system, which physically is actually interesting because you don't necessarily have an infinite system at your disposal. So here you have a quantitative way of measuring the rotation invariance. For people who don't like so much this distance between measures, just think that in particular, for instance, if you look at probabilities that points are connected to each other, this is rotationally invariant, for instance. This is the type of things that you can get. You can get much more, but this is, for instance, one thing you can get. So the rotation invariance, you don't need to go through universality conjecture in some sense to justify the existence of this rotation invariance. You get it directly mathematically.
Hugo,
yes,
your theorem, is it for any Q or is it for?
Okay, so it's for, yeah, sorry about this. So here, it's not clear for which Q it is. It is for every Q between 1 and 4. And I have a PhD student that is writing it for Q between 0 and 1 because it also works. It's just a little bit more technical. So it's already a big baby. Let's say there are already like almost 100 pages. So we thought that we should first do it in the regime, which is the simplest, and then let other people struggle with the generalization. But it works on the whole regime Q from 0 to 4. And remember, 4 is a hard barrier because above it, you have a discontinuous phase transition. So there is no rotation invariance, there is no scaling limit. It's a discontinuous phase transition. It's not a critical system.
Thank you.
Okay. So you get it for the whole regime. Let me, in the 5 last minutes, maybe, 3 last minutes, tell you just very briefly how we do it, to just give you a glimpse at the proof, which maybe
we can give you a bit more than 3 minutes if you want. I mean,
okay, so then that allows
10
me
minutes at least is fine.
Just a little bit more. So the idea is that we are actually going to do it. Let me skip that and just, well, maybe not skip that. We are going to do it by proving a kind of universality for the system. We are going to look at percolation, at Fortuyn-Castellan percolation on a class of graphs, which are called isoradiographs. So isoradiographs are graphs for which each phase is inscribed in a circle of radius 1. All of circle of radius 1. So it gives you some kind of hard constraints on your graphs, but still you have a very large families of graphs that can be embedded in the plane in such a way. And these graphs, they appear to be attached naturally to certain weights for edges. So imagine now we are not going to penalize the occurrence of an edge in omega by P at every edge, but by PE, where PE is allowed to change with the edges. PE for the edge E. Okay, so it varies with the edges. And it's a very natural class of models and graphs because they are related through the star triangle transformation. The same as for electrical networks. If you take an isoradial graph, this is the black points here with the edges to, linking them. And imagine that you find somewhere, a triangle like that. Here you have a triangle in your graph. Then you are allowed to modify this into a star here by adding a vertex and putting 3 edges like that. And if you choose the weights of your model, so here you had maybe P1, P2, P3. If you choose P1 prime, P2 prime, and P3 prime in a nice way, you end up with exactly the same model in the sense that the partition function of the model are the same, but even you can couple the two systems in such a way that the connectivity between every vertex, except of course this additional vertex that doesn't even exist on top, the connectivity are exactly the same. The probabilities that points are connected and so on are exactly the same. It's kind of a miracle out of this isoradial graph family of models. And it's not, the existence of the star triangle transformation is actually reminiscent of the integrability of the system. It's an integrable system, and this star triangle transformation is some kind of probabilistic interpretation of, if you prefer and you are more comfortable with these things, for instance, the commutativity of the transfer matrices or the Young-Baxter equation, this type of things. So here it's kind of a pictorial manifestation of these special properties of many two-dimensional statistical systems. So you can transform in such a way, you can transform one graph into another one by doing this star triangle transformation. But now imagine there is actually a special case of isoradiographs, which are, imagine that I rotated just out of I mean, to make a nicer picture later. Imagine I look at the rotated version of the square lattice. What is happening? Oh, I'm panicking. It doesn't work. Ah, okay. This is a rotated version of the square lattice. It's clearly an isoradiograph, right? I mean, every square is inscribed in a circle of radius of fixed radius. So if I increase the thing sufficiently, it's going to be of radius 1. And imagine I look at another isoradiograph, which this time is a rotated version of the rectangular lattice. It's also an isoradiograph. Well, what we are going to try to prove, and this is the object of this theorem, is that in fact, the large-scale properties of these two graphs are the same. You have universality, if you want, that all this rotated version of rectangular lattices where you are allowed to vary alpha, which is the angle here, you are allowed to vary alpha, then you end up with the same large-scale properties. I need to tell you why you do that. I will tell you in a second, but notice that in particular, if I have the same large-scale properties, notice that something happens here because this graph here has a symmetry axis with an angle alpha over 2. And this guy here has a symmetry axis with angle pi over 2 or pi over 4, depending on pi over 4. So. But that means that if the two models have the same large-scale properties, then even on the left, I should also have this symmetry axis with angle alpha over 2. But if I have symmetry axis with angle alpha over 2 and symmetry axis with angle pi over 4, I get a rotation symmetry of angle alpha minus pi over 2, something like that. And if this is true for every alpha, I get rotation invariance for every model, for every angle. So you end up with rotation invariance out of universality among this restricted class of rectangular lattices. So let me finish by just one picture. Here is how we are going to prove that the properties on one rectangular graph is the same as on the other one. Let's imagine that I take my square lattice and I put my rectangular lattice on top of it. Now here, what I can do, I can create a triangle here and transform it into a star. Then I can get here a star that I can transform into a triangle. Then I get a triangle that I can transform into a star. And I can go on until the left side. And what happens here is that in some sense, I mean, this is a picture that many of you maybe already recognize, but what eventually you did is that you exchange two lines of your lattice. And you can do that for the second line, then the third line, etc. So you can, by transfer matrices, by star triangles, you can transform one lattice into the other one by successive application of star triangle. You do a lot of them, right? Because for each exchange of one line, you do actually order n. Let's say if it's a system of size n, order n star triangles. And you need to do n exchanges for n lines. So you get n cube transformations. But imagine that somehow, I managed to prove that the loops, when I transform, they just change a little bit at each transformation. Then if I manage to do this for the whole thing, maybe I can prove that the loops didn't change so much. But if I started with loops here that are on the square lattice, I'm going to end up at the very end with loops on the rectangular lattice. So proving that these things don't change is going to actually prove that the large-scale properties of one system are close to those of the other system. And this is basically the whole difficulty of the proof is to manage to prove that these star triangle n-cube star triangle transformations, they don't change substantially the shape of your large loops. And that's what we did in this paper. So I'm sorry I went, with this big screw up with my iPad. I will punish him later on, but I hope that Steve's talk was followed, it was possible to follow it and that I didn't screw up too much. Thank you very much for your attention.
Thank you, Hugo. So we have time for a few questions.
Very good. I'm trying to find a simulation why I will try to answer your emails, your questions. Yeah, go ahead. Are there questions?
So maybe I could start. So if I understand correctly, the subtlety here is to realize the star triangle transformation at the level of configuration and not just at the level of a partition function, but you want to do it. So what are your rules for star triangle? Because you have to do some at some point some sort of probabilistic move to do this.
Exactly. This is a very, very, very good question, because indeed the star triangle transformation connecting different models, this is something that goes far back to Baxter. But here we need more than that. Indeed, it's not just the fact that the partition function are preserved. You need a configuration to configuration. So let me go up a little bit and tell you, no, I'm not going to go up. I don't have it on this slide. So there is a given recipe that you can use to match the different configuration to configuration, and it really creates a coupling. So there is a formula. It's an explicit formula. It was actually found by Manulescu and Grimet. They were the first one to use it. Probably it already appeared somewhere, but to use it efficiently, not to prove universality in some sense of really the scaling limits, but more that the exponents are the same, things that were coarser in some sense, where they didn't need to prove that loops really don't change. And what we did is really to go up to the next level in some sense of really proving that the shapes don't change. So where their thing was a much more, they only needed to prove that the drift somehow of the transformation were smaller than 1. We really needed to identify it to be 0. And there you need to be careful on how you embed the graph and so on. But these transformations, they are very explicit. It's like a table, something like 9 by 9, where you know where to, how to attach the weights in such a way that you get a true coupling. But your question is quite right. You need to find a coupling and not just identities of partition functions.
And it behaves well with respect to the distance which you have introduced. So because
they don't behave so well there. Basically what we do is that we understand that you want to understand that one step like that is going to create kind of, what will happen is that if you want the geometry of your loops, you kind of, for instance, let's focus on the top of your loop, okay? Top of a big loop. You want to understand that one step of this transformation is creating kind of a shift of this top of the loop, but you want that the shift is in average equal to 0. So you need to prove that the shift exists in some sense, that it's kind of, the transformation is going to create a kind of well-defined shift. And then you need to prove that the value of this shift, if you want, of this average shift is 0. But then, at the very local structure, actually the transformation does change the distance. It's not that nice at the local level. It's not even that nice at the line level, but in average, if you want, by a kind of almost ergodicity, it's going to create a shift which is 0, but it's only an average statement. It's a probabilistic statement. It's not deterministic that all the transformation are actually nice in terms of distance. I don't know if I answered.
Yes, I can see it.
Let me try to share just one simulation. This is, do you see the simulation?
Yes.
So here is actually a sequence of star triangle transformation that modifies one graph into the other one. And you see that the large clusters, they move a little bit, but globally they don't. And that's basically a summary by picture, if you want, of our proof. But I mean, then of course, turning this into a mathematical theorem is challenging, but this here you see at least that these star triangle transformations, they clearly don't make big changes in the macroscopic structure of your graph.
I see. Very visible.
Are there other questions?
May I make one? That's Andrea Spartiello.
Yeah.
Sure.
So, very nice idea, and thanks. I don't want to mess it up, but still, I mean, I think you could do that, despite the fact that the distance is so nasty because you worked a lot and you're good. But are we sure that there aren't simpler distances? For example, how bad would it be if I introduce a cutoff distance, and then I say that I consider k-point functions for say the 2-point function, which tells how many loops are swallowing one point but not the other?
Yeah, I mean, you can do that. So it's a much weaker distance, and the difficulty to prove that the thing is going to be rotational invariant is going to be exactly the same. So that's why, I mean, you see, I mean, once you have a proof, so we started by things like that. But once you have a proof of something, if it gives you more information that you actually seek, then you want to be using it as much as possible. So you could indeed try simpler distances. I mean, for instance, distances that for the Potts model would correspond to just correlations between endpoints, where indeed you introduce a cutoff that you only look at points at a distance, say epsilon of each other. This you can do. It's not, first, it's not that clear it's a distance, right? I mean, you need to be careful about the fact that it determines sufficiently well your system. So you add yourself a difficulty there. But second, you don't reduce the difficulty of understanding the geometry of the loops. You see on this picture, you actually, on this simulation, you see very well that kind of a natural thing to keep track of is the shape of loops. Because if you have even given points, like if you look at this point here that I point with my thing, no, once it's in the cluster, sometimes it's outside. I mean, as soon as you are going to like look at given points, actually the geometry of your percolation configuration nearby these points is going to start to matter a little bit. Not much. I agree with you that most of the quantities you are going to consider are macroscopic ones, but still you introduce difficulties like singularities, if you want, at the points, and they are actually kind of messy to work with. So I don't know if I explained well. Even the lattice is not the same at a given point because your graphs, they are changing. So a point in your graph may be moving with lattice. It's a mess. We tried, and it's actually much more messy than just keeping track of the large loops.
Yeah. Despite the fact that the loop is a fractal, it has a house of dimension which is larger than 1.
Yeah, I agree with you that this may be scary, but actually it's of no problem. I mean, this raises no issue whatsoever. It actually even helps you sometimes. So because it helps you telling that the property of a graph of a point somewhere is not so important. It also gives you, fractal are scale invariant objects. So you can even use, you don't know the full scale invariance, but you can use properties of your loops that are kind of quasi-fractal in some sense. That, for instance, typically they are rough at every scale is something that actually helps you because it introduces mixing in your system between scales, and this is helping you. So I never thought about it. I mean, that's the first time somebody asked me this question of whether fractality is a bad thing, but actually it's more of a helpful thing if I think about it.
I have hello, Hugo. This is Bertrand. I have a question, a side question. What is the present status of the same problem in the case of the FK cluster model on a random planar map?
Oh, so that's some people.
And would it help? Would it help?
Yeah, I mean, so let me.
I know you don't work on that, but
yeah. So I don't know exactly what is the status. I know that in the continuum, so let me answer it not too stupidly, but still a little bit stupidly. So first, I don't know the status of the discrete question. So you take like really FK on a discrete planar map and you try to converge. Maybe this slightly reverse engineered system that all the team of Jason, Scott, and you and everybody, like when they discretize the exploration function, maybe there they can get something, which is already a very big achievement. Then I don't know how it would help in the discrete to get the same thing for a given regular lattice. What I can say, which is related to that, is that Eng and Sun used in the continuum, they derive CLE properties, which are things that describe the behavior of really the scaling limit of a statistical physics system on a regular lattice. They used actually Liouville quantum gravity to compute these things. So they put their CLE on top of a fluctuating surface, and there things in the continuum, there things become to be much more Markovian, and they manage to actually derive if you want, the correlation properties, correlation functions of CLE, using exactly this link to Liouville quantum gravity. So in the continuum, if you want, they actually exactly use the link that is predicted. You know this much better than I do, but I mean between the behavior on fluctuating surfaces and behavior on lattice system. So there, the Eng Sun is actually exactly achieving this thing in the continuum, which, by the way, I find it's a very, very beautiful result.
Thanks.
May I ask a question somewhat related to Bertrand, and something you mentioned on your slides? You talk about strategies to prove conformal invariance. Yeah. And in the first strategy you showed, you said that you have to prove that scaling limit exists. Yeah. And you said that it's difficult in general. But in the context of maps, I don't know what sense you would that scaling limit exists, but people are usually not worried about existence. That is, you take subsequential limits, so you have compacity. But then the difficult question is to prove uniqueness. So I was wondering if it's exactly the same problem you have for lattice model.
Yeah, it's a very, very, very good comment. I mean, that you are making. That it's exactly. I mean, the subsequential limit. It's very easy to get. You get. I mean, sorry. It's a result of Eisenman and Burchard. You have a pre-compactness criterion, and you can check it satisfied. So. So this is not the difficulty, and indeed it's a uniqueness which is important, because when you try to prove translation invariance is obvious, actually, even without any subsequential limit is translation invariant. But if you want to prove scale invariance, you need to say simply, I start from my guy on Z2, and I start from my guy on lambda Z2, and I do the same thing. Or if you prefer, I start with delta Z2, I let delta tends to 0, but then I need to check that if I, let's say delta n in such a way that it converges, if I take lambda delta n, it's also going to converge, but I would need that it converges to the same object, and then I just deduce, well, then it's scale invariant by a factor lambda. So uniqueness is exactly what is going to give you scale invariance. So you're entirely right. You can just take subsequential limits. This is fine. But the difficulty is the uniqueness, and this is the one that gives you actually scale invariance.
I see.
Yeah. So it's the same problem. Yes?
May I intervene again? That's Andrea again.
Yeah.
Sure.
So you said that the idea that you showed us of the green and pink parted swap, they are essentially the permutation of transfer matrices, T with parameter P, T with parameter P prime.
Yes.
And you do with that rotation invariant.
Yes.
And in order to prove that there is a continuum limit, something that you could use in principle, if I'm not wrong, and with many question marks, is that T of P and T of P prime commute among themselves because they also commute with the Hamiltonian of the model.
Yeah.
And the Hamiltonian is in the continuum. So imagine that instead of swapping TP and T prime, you swap a bunch of TP and a continuous evolution with Hamiltonian.
Yeah, so it's a good comment, but it's only, I mean, it's continuum in only one direction for the Hamiltonian. So it's still a discrete system. Actually, it commutes, but the intrinsic scale of your system is exactly the same as one of your discrete models. It's not a continuum limit. What you would need is actually to take the limit on also in the scaling limit also in the Z direction.
But you can commute also the vertical transfer matrices. I mean, they're not transfer matrices, they are spectral lines.
That I'm certain about it. It's the intrinsic scale of these systems is always the same one. There is no known transformation that I know of, and it includes, I mean, I know very well about the connection to the Hamiltonian of XXZ.
I agree that there is no way of doing that within isoradial. It should go beyond the isoradial.
So then there is no connection between, I mean, there is no connection between basically systems. I mean, there is no equivalent of star triangle or things like that that connect systems at different scales. There is none that we know of. If we would find one, it would be actually, as you said, a very good strategy to try to prove existence of a scaling limit. But we don't have this. The connection to Hamiltonian, the fact that the representation of the Hamiltonian or the fact that Hamiltonian XXZ is indeed continuum in time is not an indication. It's a special case of isoradial, which is a limit when you squeeze basically the rectangular lattice to when you make it alpha
to lozenges which are very thin.
Exactly. But that doesn't change the scale, unfortunately. We tried because we thought then we end up with something continuous in time. Maybe there is a way to, at this place, slightly change the scale and then go back to the system, to the discrete system. That's a very natural thing to do, what you suggest, but we didn't manage to do anything there. Basically, it seems that the transfer matrix is really mostly giving information on systems of the same scale. What we did notice is that the spectral properties of this transfer matrix, when you plug in the rotation invariance in a strong way in the system, for instance, if you look at 6 vertex height function and you use the rotation invariance of those guys, it seems to be saying a lot on the spectral properties of the transfer matrix. So there you have a chance maybe to prove that they are scale invariant in some sense, and then to get GFF. Yeah.
Sure. Okay. You cannot do that with isoradial. And if you say transfer matrices really do exactly isoradial.
Yeah, they correspond to isoradial.
There is a question by Vincent Pasquier next to me.
Yeah.
Just, I mean, but maybe it's on the spectrum. Do you see somehow some indication of how the universality class changes when you change the parameter Q in your model? I mean.
So you have different ways indeed of seeing the thing. So what is going to happen in the transfer matrix side? On the transfer matrix side, there are different ways of seeing the sigma, but let me mention the one that is the most related to the thing, is that when you rescale so you take the biggest block of your transfer matrix, the block that is going to correspond to a system without any excitation, that you have too many up or down arrows in say 6 vertex. And then what you do is you don't look at the very top of the spectrum that would actually contain information about the universality class and what physicists usually look at. You look in the bulk, meaning you look at eigenfunctions that converge to the Perron-Frobenius one when you take larger and larger systems, but not like the very top ones. And those eigenfunctions, we managed to prove that in some sense, the space, I mean, we think we will manage to prove, let's put it more like that. But I mean, at least if you are allowed to a few very simple assumptions, then we prove it actually. You will manage to prove that somehow the counting measure of those things is going to be like Lebesgue. if you do things properly. But it's Lebesgue times a constant, and this constant is actually reminiscent of the variance of the height function you will end up with at the end. And this is actually very much related to the universality class. So you will converge to sigma square times Gaussian free field, where sigma square will depend on the value of Q if you want, which is exactly what you expect in some sense in when you do bosonization or when you try to relate to height function your spin systems. There is a natural way that the variance of your GFF is varying with the universality class. And this we managed to see in the spectral properties of our system.
Thank you, Hugo. Are there other questions in the chat, or you can unmute yourself to ask if you want?
A last tiny one. If it is too long, just stop me. Can you implement any other conformal transformation, like some Möbius transform with this trick?
It's a very good question. So we still have the problem of the scaling. So unfortunately, if you remove scaling from what you can do, it's very bad. And these isoradiographs, they are in some sense lattices that have, I mean, they are not necessarily lattices, they are graphs, which really have a given scale at every place in the graph. And it's always exactly the same. So it's not coherent, right? I mean, the only possible transformations you could make that would preserve the scale are going to be the translation and the rotations. As soon as you take any other conformal map, it's going to somewhere modify locally the scale by f prime of z, right? Absolute value of f prime of z. So this will make you immediately out of the isoradiograph regime. Let me mention that there is one case where people know how to do that. It's in the case of the easing model. There are very impressive works by Dimad Chelkak in particular, and many of his co-authors, where they generalized isoradiographs. And that allows for this kind of, if you want, change of scale depending on the place of the lattice.
So you have to generalize that.
Yes, but it's not, I mean, easing is a very enjoyable system, right? It has a lot of additional integrability properties. So whether this type of things even exist for general integrable system, it's not that clear.
Okay, so unless there are more questions, we can thank Hugo again.
Thank you very much for your attention, and sorry again for this this bad.
Well, in the end, you.
Thank you. You did well.
And we could see your simulation, which was really nice.
Yeah, that I'm happy to have been able to show it. Thank you very, very much. Bye bye, everybody.
Bye bye. See you.